We'll just present my screen and then we can start. So is this the usual number for the session these days?
Yes, ma'am.
Okay. So today we are going to focus on week 5 and week 6. We'll revise all the topics. We'll not go into the proofs. We'll look at everything that we have seen in week 5, 6. And there are a few questions that we'll solve at the end from these topics. So in week 5 and 6, basically we are doing regression. We are looking at the regression. And the data that we had seen for regression was my input data was my x1, x2 till xn, where each x's belong to RD, right? And the output that I had was y1, y2 up to yn, right? And each of these yi belong to R. Now, so our goal was to like learn this function, right? So our goal was to learn this function h, which was defined from RD to R. And by learning, we mean that like on our training data, our input data, training data will learn this model, and then we will try to see how is this model working if given any new feature, right? Given any new data set. So uh, basically we want to learn this function, what this function is. And once we learn this function, we also want to check how good is this function. So in linear regression, what we try to do is, so we want to fit this data set, right? So to check whether how good your model is or your function is, there is something that you calculate and we call it as error or loss function, right? So you calculate the error or the loss function, and we say that this is given by sum over I varying from 1 to n h of xi minus yi whole square. Okay? This is what we do. So, and what we want is when we are talking about the linear regression, we are talking about the linear structure. Basically, we want to look in the linear space. So there we define our h of xi in linear regression as w transpose xi. And this is what we define. Now, our goal is that we want to minimize this error as much as possible. Correct? So we want to minimize my sum over w transpose xi minus yi whole square, I varying from 1 to n over w which belong to RD. And these w's are the weight vectors that we want to um, uh, estimate, right? Basically. So this is our objective
Hello,
function.
ma'am. What is W here?
W are the weights vector, like any simple linear regression model that you would have seen, I think in MLF also. So you write, no, W is equal to, let's say, W1 x1 plus W2 x2 plus up
Okay.
to Wn. So there was example of price of a house, predicting the price of the house based on certain features. So you want to learn this WIs and see which one fits your data set, right? These are the weight vector that you are learning. Now, um, what we want is to minimize this. This is what we want. So this is my objective function,
And
and
how far we have covered till now?
we have just started. We have basically not looked at anything.
Okay.
So, all right. So this is what we said is my linear regression problem. Now, so if you write this in terms of the matrix, so what can you write this as? Minimize W over RD. W belongs to RD. So this term, we know we can write it as norm of X transpose W minus Y square L2 norm. This is what we can write this problem as. Now, what we get from here is we want to minimize W, we want to minimize this X transpose W minus Y transpose times X transpose W minus Y, right? So we want to minimize this function and we want to minimize it over W, where W belong to RD. So we know that to minimize any function, what we do, we take the function and we find its derivative, set it to 0, and then we can find the unknown. So in this case, our unknown is W. W is something that we are trying to look for. So since this is a vector, so it's not no longer going to be derivative. It's something that you're going to find is the gradient. So we find, if I say, let's say this is my f, f of w, then if I find the gradient of fw and equate it to 0, so the w that I find, or the optimal w that we get, is something of the form xx transpose inverse or the pseudo inverse xy. So what we got is, this is the solution to this optimization problem. So this W star satisfies this optimization problem. Now, what we say is, uh, so, all right. So this is the W that we got. Now, when we try to see like what, like where does W star lie, or how does W star looks like. So what we had also observed that this W star lied on the, so this W star or W star lied on the subspace, lied on the span of the data point. We are not going to do the proofs and all. I think these are some results that we had obtained from the lectures. So this is something, one point that we had seen. What we had also seen is that if you take X transpose W star, then this X transpose W star is nothing but the projection. This turned out to be the projection of yi's onto the subspace spanned by the features. Spanned by features. Right. So what is our feature vector here? So we have X transpose, right? And how did the X transpose look like? So if you have, let's say, F1, F2, and so on. So what we had seen is, like, if we just take two features, and if we talk about, if we take a linear combination of these two features and any label y that is in R3, if you take the projection of this, let's say this is my feature space. So any y that we obtained, any y that we take, and if we projected it on the feature space, then we had gotten this point over here to be X transpose alpha star, where alpha star was nothing but your W star. And W star is the optimal solution for your linear regression problem. So this is also one thing that we had seen, um, like while doing the linear regression problem. Then what what we had also like what we okay, so next is, like, generally, like when you solve this linear regression problem, so where W star is your XX transpose pseudo inverse XY, right? So if you see it over here, so your X is what? Your X matrix is D cross N, right? How does this look like? This is uh, X1, X2, so on till Xn, right? So you have a D cross N matrix and X transpose N cross D. So when you find this W star, like this optimal W, so sometimes computing it might be very expensive, like, yeah, because it involves like in case your D is very large, then in that case computing this inverse is going to be very expensive, because you have to do the inverse and then product everything. So to deal with this, we can use some optimization techniques. So the optimization technique that we saw in the lecture is what we call it as gradient descent. Gradient descent, right? So in gradient descent, what we the update rule that we had used for finding the optimal W star was WT plus 1 is equal to WT minus some eta T, eta transpose, basically, grad of F of WT. F of grad of W, F of WT, right? So this is the update rule that we had seen, where eta was the step size, right? And this T here, basically, it's indicating iteration. So you start with some W and then you keep updating your WT plus 1 using this rule, unless this unless you it converges. So using this gradient descent is one way we can tackle this problem of computing the inverse, because when you look at this gradient here, it doesn't require any inverse computation. So our original problem was what? Our original problem was x transpose w minus y ka norm square, right? I mean, we wanted to minimize this function over r over w. Now, when you take the grad of this, the grad of this turns out to be grad of this turns out to be 2xx transpose w, 2xx transpose w minus 2xy. So it doesn't require you any inverse computation. So this is where it is useful. So there are other methods also for optimization. Something like Newton reaction is something that you can use also. So we'll stick to gradient descent for here. Then like
Which method you told, ma'am? Newton reaction.
Newton reaction, yeah, but not
Okay.
required here. Okay. So all right. So this is the update rule for the gradient descent method. This is your update rule. Then this was like to deal with when your D is very large and the inverse computation is going to be very expensive. But in case your N is very large, then how do we deal with this? So what we can do, if your number of data set itself is very large, then we can adopt something which we call it as stochastic gradient descent method. So you have another uh, optimization technique which we call it as stochastic gradient descent. So in stochastic gradient descent, what we do is um phase, yeah.
Actually, ma'am, I want to know about the direction of gradient descent. I'm little bit confused with the direction of the gradient descent.
Direction as in
In some question, I saw that question asking for direction. What would be the direction if I
mm,
will take in second iteration or third iteration?
okay. Can you put the question in the chat if you have any for
Okay,
the
ma'am.
difference?
You can continue. I am posting it.
Yeah, yeah, I'll continue this and later we can take this question. Okay. So in stochastic gradient descent, what we do is like we take a batch, a small sample, you can say. So we take a batch of from the sample, and then we perform and we kind of think of that batch as a entire sample, and then we perform the gradient descent over that sample or over that batch. And this is what basically your stochastic gradient descent is doing. So let's say you have total of n data points, but n is very large. Then you pick a small batch of, let's say, some sample of size k or something. Okay. Then on over that sample, you perform your gradient descent. And when you perform that, according to the update rule, what should you get? You should get your WT plus 1 to be WT minus eta eta transpose grad of. So this was your grad of F of WT. But now when you are restricting your entire data set to a smaller sample, then in that case, your X will also change. Let's say it is X dash, and your Y will also change, right? So let's take it as Y dash. So when you take the grad of F of WT, you will have 2 times maybe X dash X transpose dash or X dash transpose WT minus 2 times X dash Y dash, something like that, right? So you do it for different samples. Let's say you do it for T or different batches, you do it for T batches. So at the end, what we do is every W that we obtain, we take a like an average of all these Ws. So the final weight, the optimal weight that we obtain using the stochastic gradient descent is something as, like, let's say if I take different T from 1 to let's say capital T, then it will be 1 upon capital T sum over Wt that we obtain from each of these small batches, and your T will vary from 1 to capital T. So in stochastic gradient descent, you take the average of all these weights, and that is what you obtain as the optimal W star. So these are some of the optimization technique that we saw to deal with the, like, in case the computation of W star is something which you are not able to work out for. So there are some, these are two optimization technique that we saw which can be used to find your W star. Then next we moved on to the kernel regression. So the same as what you had seen in PCA where we kernelized a function, here also we are going to see something similar. Um, so, okay, so this was switched off. All right. So in kernel regression, see, what we had seen was W star is equal to X alpha star, right? This is what one result that we had obtained. And this X alpha star was just some vector. So we'll not do the proof. So what we had, like what we do in kernel regression is, like to, in kernel regression, basically you map your data point to a higher dimension. You perform the linear regression over there, and then you find your optimal weight vector. And then for any new test data set that you get, you you find the W star on like even the new test data set, you map it to the higher dimension, and then you find your label for that.
Ma'am, we go
So
to higher dimension to find linearity, right?
yes, to find the linearity, correct.
Okay.
So when we were doing the kernel regression, so what we had seen is your W, W something, W star transpose. We had obtained W star. So W star transpose phi of X text X test, right? So any new test, any new data set that you get, test data set that you get, you take it to the higher dimension, and then when you do W star transpose, we had gotten it something like alpha I star times the kernel function, right? Like if you have any new data set and you have to predict what label this data set will take, then this is what we had seen to find out um, to find the prediction for this test data set, right? And this is my kernel function. This was my kernel function. And if you remember, there are two kernel functions that you had seen in week 2. So one was your kernel of the form 1 plus x transpose x dash maybe some to the power p. This was one kernel function. And the other we had seen where Yeah. So what was the other kernel function that you know?
Gaussian.
Gaussian kernel, right? And the Gaussian kernel was defined as, I think, 1 upon e to the power minus xi minus xj square upon 2 sigma square, something like this. It was defined, right? I guess. I think this was the Gaussian kernel. Okay. So these are the two kernel functions that we had seen. And what is this alpha here? So, okay. Your alpha was defined as k inverse y, right? Okay. So if you have to predict for any data set, this is how we could do it in kernel regression. Now, after the kernel regression, we saw the probabilistic setup of the linear regression model. And what was that? So what we said is your suppose I mean your x was in RD and your y was in R. Right? This is what we know. My data set was something of the form x1 y1 comma x2 y2 up to xn yn. This was my data set, and what we had assumed is, let us say that my y given x, this follows y transpose x plus epsilon, right? And this epsilon is the noise, and this noise was uh, distributed as a normal distribution with mean mu and variance sigma square, right? And if we when we wanted to and our goal was to estimate, our goal here, like if when you see this linear regression as an estimation problem, so here what we want to estimate is rw. So if my epsilon was normally distributed with mean 0 and variance sigma square, I can say that my y is also normally distributed with mean w transpose x and variance sigma square. Right? This is what we can say. So, like we know to solve any this is uh, now we are thinking it as an estimation problem. So in the estimation problem, we know a very popular method which we call it as the ML estimation problem, right? So we think of it as an like it is an estimation problem, and we are trying to now find W hat ML. So our goal is now to find W hat ML. So when we in order to find this W hat ML, what we do is we find the likelihood function, and from this likelihood function we can take the log likelihood, because log likelihood is easier. So we took the log likelihood, then take its derivative, set it to 0, and the W hat ML that we found over here. We'll not go into proofs, no proofs here. So the W hat ML that we found um, for this estimation problem was nothing but W star that we had originally seen for our linear regression problem. And this W star is nothing but XX transpose inverse, let's stick to inverse only, x transpose inverse xy. And this is the same solution that we found for a um, using the squared error thing, right? So when we so what we can say from here, we can say that like when we assume this Gaussian noise, so this noise we assumed it to be Gaussian. Now when we assume this noise to be Gaussian, solving this estimation problem is nothing but the same linear regression solution that we've found using the least square error, right? So one more thing is like this once you change this noise, the solution will also change. So that we'll see later. So it's basically depending on your like it's like your noise is pulling is actually important over here. Like how is this noise distributed? So now, like after this, like once we found what our ML estimator is for this linear regression problem, then we wanted to see like how good is this estimation problem, right? So my W hat ML, we wanted to see how good it is. So what we know is my epsilon, um, my W is a random variable, right? W is distributed as a normal with mean W transpose X and variance sigma square. This is how W is distributed. W is random, so any sorry, Y is random, so any W that you get, W hat ML that you get, is also going to be random, right? So if these W's are going to be random, um, what we can check from here, like you take this was with respect to a particular data set, you can say, right? Now you change your y, you keep getting different w's. So what we do is, in order to check how good your w hat ml is, we kind of find the expectation, like we want to see that in the long run, or yeah, in the long run, how well your W hat ML is performing. And for that, we know we can find the expectation because W hat ML is random. So we want to check what is the expected value of W hat ML minus the true W. Your W is a true W. Sorry. So we want to see how good this W hat ML is. So in order to check that, we are going to go ahead and find the expectation of this norm, right? And what we saw that this expectation was sigma square times trace of xx transpose inverse. This is what we found, right? So now the question is like, how do we check the goodness of this estimator using sigma square and trace of xx transpose inverse? Now, if you look at it, like sigma square is something that we cannot do anything, but here there is some scope. Like we would want this, we would want this term to be as as less as possible, right? What is the need of expectation? So expectation we are using to like see how your W hat ML is performing. Okay. So for that, like we want to, so now the proofs have not been given. I hope the proofs were shared to you, and you have seen this, but proofs are not required at this point of time. So what we'll see now is Oh, okay. So what we will see now is what is this trace of XX transpose inverse. So in general, like what we had done was like we for any matrix X. Yes, Sudhir.
Ma'am, this W at ML is best W for our data set, right?
W hat ML is the best W for our dataset. Yes.
Then you're saying that we are trying to find the expectation of W at ML, uh, the norm of this thing, W at ML minus W.
Okay. See.
Then from
See.
where these data sets are coming, ma'am?
See. You
Because
have
for
to. This is the probabilistic view of linear regression. I mean, here in this case, now you have to go back to your maybe stats 2 and think of it from the estimation point of view. Okay. So when we were doing the estimation, we did one kind where, so here our goal was what? Our goal was to estimate this W, right? Our goal was to estimate this W. Now, in order to estimate this W, we use this ML estimation method, and we found that this problem, I mean, the solution that we had is same as the least square error. I mean, the same W that we obtained from the least square method, right? But now here, I mean, data generation, how is this all coming from is not coming here. I mean, it's not required. So like depending on like what your epsilon is. So epsilon is the noise, right? So there, even you are fitting the noise in the data set, right? So what W, like the W hat that you estimated, W hat ML, we just want to see, like if any estimator that you find, you want to know like the goodness of the estimator, no? Like you want to check its bias and so on. So here also we want to check this goodness of this estimator W hat ML. Um, access 2341. Okay, this is something different.
Hello?
Yes, Harsh.
Yeah, can you please just tell me what, if the given data set X is 2341, then what is its X60? Is it like 2341 into 2431? And what is its XY? Is it like 2341 into whatever the column vector which they give? Like, what will.
What? You are saying excess. This is not of what we are discussing right now, right? There's something
No, no,
else.
no, it's the same, right? Actually, like there you have X60
Okay,
and then
okay. I mean,
XY.
No,
okay.
you
So
can
what?
calculate it. You can calculate it. It's only dot product. It's only dot
No,
product.
no, I understand. Can you please tell
You're
me
you're
what is X
saying
there?
okay, okay. So X is 2341, and X transpose is just now you'll have a column vector.
No, what is X transpose for that? 24, uh,
No, you have to now
2431.
think of it as row vector or column vector, right? Because what you have written is X is equal to 2341. I'm assuming it's together or it's
No, no, it's different. 2, 3 is in one row, and then 4, 1 is in second row.
okay, okay. So your X1 here is your 2 4. X2 here is 3 1. I'm talking about small x1, small x2.
Yeah, can you tell me like what is X60? Can you just write it in?
X60, so X is this matrix. Um, so your X is 2 3 4 1. What is XT? XT is nothing but X transpose, no? 2 3 4 1. That's all.
So okay, X60 and XY is suppose
What is your Y?
Y is
So Y
uh,
will be some R2.
yes 2 4.
So
Suppose y is 2 4 for the first question.
Okay, so 2 3 4 1 2 4.
Okay.
Yeah.
So is this how it is? Okay. So when I tried this, the answer which I got actually didn't match for the question which was there in the question paper. Actually, that's why I asked. Actually. Is it like this or is it the ulta of this? The x is 2 4 3 1 and then xt is this one actually. Is it xtx and then xty?
Mm. Oh, you're saying is x this or is this x?
Is x that and then xt is that. In case if they given the
I
question
think in
like
the
that.
question it should be mentioned, no?
No, in the question they have given it as 2 3 4 1. Okay,
Can
like
you?
how you're written. But should we take x as 2 4 3 1 and then xt as like this? If you take it like that, then you get the correct answer. Like whatever matches in the question paper, previous question paper.
If we take it like this,
No, if you take like this, you don't get the answer. If you take it the
is it?
ulta, if you take that as 2 4
I'm
3
sure
1.
there must be something else mentioned the
I
question
guess
paper.
in that question paper it may be mentioned n comma d. It is in the form of n comma d maybe. That's why like
No, R is D cross N. That is
oh
X belongs to R of D cross N. And
D cross N.
yes. And then Y is R of N cross 1.
That is fine. So this is your x1. This is your x2. Right? You have two features. I think this is how we have. I mean, these are the notations that we have used in the lectures at least.
Okay. So if you do like that, then you get wrong answers. If you do like this, then you get the right answer. So that's why I want to
Maybe answer is wrong.
Yeah, that is
No,
also
it's a
one
September
possibility.
2023 paper actually. And then
Answer might be wrong. It's okay.
Okay. So the second question is if it is not a 2 cross 2 matrix, if it is a columnar matrix, minus 2, 3, 4 x's, and then what is x? You'll consider it as a horizontal vector or a vertical vector.
What?
If for the second question, this is first question. Second question is x equal to minus 2, 3, 4. Then what is
No.
xt? Can you
What
write
is
beside that? If x equal to minus 2, 3, 4, I've written.
x is equal to?
Yeah, minus 2, 3, 4. Minus 2.
This?
It would be 29.
Minus minus 2 3 4 in a straight line, horizontal line. Minus 2 3 4.
Okay.
Yeah, and y is minus 15 18 24 in a vertical line.
You just take the dot product, no? xy would be just the dot product.
So xt here is actually like the vertical vector, right? Is it? Xt is minus 2 3 4 in vertical, is it?
Oh, x. Okay, so this if this is my x, you're saying okay, if this is my x and this is my y, so x transpose is minus 2 3 4. This
So
is what
then
you're
this
asking.
becomes a dot product. Then when you add, say, suppose lambda is 3.
No, how does x transpose y if you do it? It's not dot product, no?
No, it's not.
Mm-hmm.
Okay, so these are the two questions actually. So
Okay, so
the
there
thing
are.
is actually I am able to get the answer, but actually you have to do two different ways. So here, in the first case, you have to take x as 2 4 3 1 and then xt as this, then you get the right answer. And in this case, you have to take x as x only, like how they have given, then you get the right answer. So that's why the discrepancy.
Okay, so there are 3 sessions dedicated to the previous term questions. I'm sure. So
No, that's
you will
fine.
more
Actually,
get
in the
more
formula,
clarity.
what you will take
Yeah.
it is what my question was. Like in
Okay.
x60, what you will take it like whether the given x or will you transpose it and then take it as the given x in x60? Not just here, in everywhere actually, like the same thing repeats, right? It's a covariance matrix, right? What do you take it, because it is not matching? Not just here, actually in other question papers also it's the same.
Okay.
Can you please get back if you
Maybe I can check some question papers and
yeah, if you can
just
get back also is fine, actually, by mail or
okay. Yeah, sure.
What's your mail ID?
You can put your mail ID over here. Okay.
No, actually.
Or Discourse is a better place to do it, I think.
Okay. How does it work? Like, can you send your mail ID like here? Then I can send a mail to you.
All right.
Thank you.
Okay. Let's get back to the discussion. All right. So we were at okay here.
Expectation.
So we wanted to see this term, which is sigma square trace of XX transpose inverse. So what we use over here is like if we assume, let's say for our matrix XX transpose, if we have some, since this XX transpose is going to be your D cross T matrix, so I will have some D eigenvalues to it, right? And if I take the inverse of this matrix, then I get the eigenvalues to be inverse of those eigenvalues, right? So if we said that all the eigenvalues for XX transpose matrix XX transpose was, suppose my lambda 1, lambda 2 up to lambda d, then the inverse, then the eigenvalues for this inverse matrix would turn out to be 1 upon lambda 1, 1 upon lambda 2, so on till 1 upon lambda d, right? This is the eigenvector that we get. So in that case, the error that we get here is this term. So here we are trying to see how much error do you have between your estimated W hat and your true W hat, right? So this error we wanted to minimize. Now this error turns out to be now after putting this trace value, we get this to be equal to sigma square, where trace of XX transpose inverse is nothing but trace is just the sum of the eigenvalues. So sum over 1 upon lambda I, where I varying from 1 to d. So this is what we got, right? And what we also observed is, like, if we introduce another estimator, like some other estimator, let's say W hat, um, uh, we had said, okay, let's say W hat R, which is basically the ridge estimator. Then W hat R, if we took to be XX transpose plus this lambda I inverse XY, okay. So if we want to, if like, we can forget about this for some time, and what we'll see is, like, once we took this new estimator, then we want to, like, in a way, want to compare this W hat R with W hat ML. So if we had any matrix XX transpose, we saw that lambda i's can be my eigenvalue. But if you add something to it, so if you add, where lambda is just some constant, so when we added some constant to it, what we will get is that my eigenvalues will just get added by this term. So if initially the eigenvalue was lambda 1, lambda 2 up to lambda d, Now my new eigenvalue will be lambda 1 plus lambda, lambda 2 plus lambda, so on to lambda d plus lambda, right? So if we take the inverse, this also, I mean, the eigenvalue for this new matrix, the trace for this new matrix, basically. So if we talk about the trace of this new matrix, then this trace turned out to be sum over 1 upon lambda I plus lambda, where I varying from 1 to d, right? So this is the, and when we found this error, so when we tried to see this expectation of this w hat r minus my true w, the square, when we try to estimate this, like this difference in the true value and the estimated value, then in that case, this we got it as sigma square sum over 1 upon lambda I plus lambda, I varying from 1 to d. And we know that this error, this error is lesser as compared to the error that we had gotten for the my ML estimator, right? And that was sigma square sum over 1 upon lambda I varying from 1 to d. And this was my mean square error of W hat ML. So this new estimator is, in a sense, reducing your MSE, right? Mean square error. It's reducing your mean square error. Now, this new estimator that we have is something that we can obtain from my Bayesian estimation problem. Like for W hat ML, we had done the ML estimation problem. Now, the way we had obtained this W hat R is through the Bayesian estimation. So in Bayesian estimation, like what we have is W hat R is equal to XX transpose inverse XY. This was my W hat R. Now, when we want to do the Bayesian estimation, when we want to do the Bayesian estimation problem, then in that case, apart from the likelihood function, which we get from the data set that you have observed, we also needed a prior for the parameter, right? And our goal is still the same, is that we wanted to estimate this W, right? So if you recall, in Bayesian estimation problem, we needed a prior for your parameter, and we had said your parameter in your Bayesian modeling was not a constant, but it was a random variable. So when we assume this prior for W to follow a normal distribution with mean as zero vector and the covariance matrix as some gamma square I, right? Then the posterior, I mean, likelihood function you can work on. So the posterior that you get, so the posterior was posterior is proportional to likelihood times prior. So we work on the posterior, and once we get the posterior, so the posterior was okay, let's not do this. So what we said is we have the likelihood, and the likelihood was coming from where? You have W given X, which was normal with mean W transpose X and variance sigma square, right? So, and for simplicity, we had taken the sigma square to be 1. So when you found the posterior, we only found the posterior distribution, right? But when we had to actually come up with the estimator, now we just have the distribution. Now, how can we estimate this distribution? I mean, how can we estimate this parameter? So there were two popular method that we had seen. One was you can, if you have found the posterior and if you know what your posterior look like, you can take the expectation and that can be one estimator for one estimate for your parameter. But here the posterior that we get did not look very uh, did not look something which can um, go into certain class of distributions. So the other way that we could do it was using the map estimate, right? And that was maximum a posteriori. So using the map estimate, so what we had seen was, so what is this W hat MAP? This W hat MAP is nothing but you try to maximize now your posterior. Okay. So when we tried to, when we did this, so the posterior was looking something like minus yi minus W transpose xi square minus 2 norm of W square by 2 gamma square. Okay, where I varying from 1 to n. So I have not worked out the proofs anywhere, but for you to understand it, like how is it coming, I would suggest, if you have not looked at the proof, please look at the proof also once. Okay. So so this was the maximization problem. I mean, this is how we find the W hat MAP, and this W hat MAP is nothing but arg of max of the posterior distribution. So now if you see, there are minus sign over here, so you can, we were able to write this as minimization problem also, right? And how can we write this? This can be written as, we can just remove the minus sign and we get wi transpose xi whole square divided by 2 plus norm of w square by 2 gamma square. So this is my W hat MAP, and we called, so once we have this, I mean, this is how we find the W hat MAP. Now here you have to minimize this function now. So once you minimize this function, the W that you get is going to be your, the new estimator, which is W hat R, W hat ridge, basically ridge regression. So the W hat R, after solving this problem, the W hat R that you get is XX transpose plus 1 upon gamma, not, yeah, gamma square I chi inverse times x5. So this is how we had gotten this estimator, this new estimator. And what we had seen is that the mean square error for this estimator is lesser as compared to when we were looking at the ML estimator. So, okay. So, in short, so so what we saw that for the linear regression, the W hat ML, where we were trying to do arg min of my W transpose xi minus yi whole square, I varying from 1 to n over W. This was my W hat ML. And the W hat R was arc of min over W. W transpose xi minus yi whole square, I varying from 1 to n plus lambda norm of square, norm of W square. And this lambda is what we refer to as ridge penalty. So in ridge regression, what we are trying to do is we want our W's, we want our weights to be as close to 0. We want to push more and more W's to 0. So if there are any like if you have a lot of features and we want to just we just want to like get rid of, in a sense, any redundant features that you have in your data set. So that is what your rich regression is trying to do. So okay, so when we saw it geometrically, like how this ridge regression solution and W hat ML look like. So what we saw is your W hat ridge was on a circle, which was, so this was on a circle. So this is my W hat R, this is my W hat R, and my, let's say this is my W hat ML. We had um, doing some like some maths you can do here, and we had obtained this elliptical contours around this W hat ML. And what we had said is, like, the point where this contour touches the circle, that is where we're obtaining our W hat MR, W hat R, W hat ridge solution. So, and what was this circle? The circle was, I mean, the circle contains a set of all the W's where your norm of W was less than some theta value. And what we had also seen that this theta dependent on your this penalty, this ridge penalty. Geometrically, this is how it looked like. But like moving forward from here, one more thing that we saw, that in ridge regression problem, like we are trying to push more and more weight vector to be as close to zero, but it is not, I mean, it is not entirely zero, right? So for this we have something, we introduced another regression problem, which we call it as the Lasso regression, and which we also call L1 regularization method. So there, the only change in this objective function was that we changed our this regularizer term. This regularizer term, we changed it to lambda L1 norm of W, right? And if you remember, this L1 norm of W is given to us as sum over, like, take the absolute value of each of the Wi's, where I is varying from 1 to D, right? Because W's belongs to RT. So this was the only change, like this we called as L1 regularization. And our problem is the same. We want to minimize this objective function, where now the regularizer term has changed, and we want to see what what is the set of W, and where did this W hat L lies. We'll call this as Lasso W hat Lasso regression. So when we saw that, I mean, when we try to say it with, geometrically, what we saw is that our W hat ML, sorry, W hat L lied on this the corners of this circle. Can just, I mean, these are not the proper figure, but this is something geometrically it looked like. So here, as we can see, at least on these four corners, this is just a 2D space, so here we are not able to see it properly. But in a sense, what we are trying to like say is like, when we are doing the lasso regression, your more and more W's are going towards the zero. So as it is evident in the 2D case here, that if we look at these corners, in these corners, your one what do you call it? Your one W is going to be zero. So you're pushing. You are sure that there are some W's which are going towards zero. So any redundant features that you have in the data set, that can be avoided in a sense. So this was about the regression problems. Then then one more thing that we seen in week 5 and 6 is like we talked about this lambda, right? We found this, we have introduced this new term which is the lambda, and we call it as the penalty term. So there are, like how do we choose this penalty parameter is something of interest. And these penalty parameters, these lambdas, we can, you can uh, to estimate this. What you can do is use the cross validation for these lambda. So for these lambda, we used cross validation, right? Uh, and what are the methods that we saw for the cross validation? One was the k-fold cross validation, and the other was leave one out cross validation. These are the two methods that we seen for um, like deciding which lambda to choose for. So in k-fold cross validation, where what we are doing is, let's say you have some n data point, and you want, um, let's say you want to perform a 10-fold cross validation or a 20-fold cross validation. So what you do is you divide your data set into k equal parts basically, and in if you divide your data set in k equal part, then for k minus 1 folds, you use use those sets which are there in those k minus 1 fold for the training set, and the remaining 1 fold you use it for um, validation. To test the performance of your mm, to test use it as validation set basically. So you have k folds, so you will have to run it for k times, because every times the number of folds will change, and then you get training set changes or validation set changes. So you calculate your loss for each of this training set, and then you take the average of the loss, and the lambda that gives you the least loss, this is the lambda that you go for. So ideally we mean there are uh, you can use these, you can I think in codes it's easier to show like how can you choose these lambdas, these penalty parameters. um, but this is the idea, like what we do in k-fold. And when we talk about leave one out cross validation, there we take um, each and this is generally preferable for smaller data set, where you treat each fold as one fold as validation, and like one data point as validation, rest everything as training. So each data point act as one fold over here. That is the only difference. So Yeah, so that was all about your week 5 and 6. I mean, the topics that are there and overall what we had seen in week 5 and 6.
Okay, ma'am.
So now what we will do is, so I just summarized like very quickly, like what was there in week 5, 6. And now what we'll do is we'll solve some problems. So let me just think. Okay. So this is our first question. Just give me a minute. Okay. Question number 1. So for the linear regression problem, you have the training data set given to you. And it is also mentioned that this data generates, the way this data set has been generated is linear and deterministic. So there is no noise. And suppose an ML engineers train a linear regression model, and the and they obtain the W star to be 3 comma minus 5 for this data set. So you have to check whether is this claim true.
Ma'am, what is the meaning of it is a given that the phenomenon that generates the data is linear and domestic?
So all it means is that there is no noise involved. That's all. You can ignore that. Not important here.
Okay.
So can you solve for this and let me know whether this solution, this the W star that has been obtained, like the engineer is saying that this is optimal weight for this problem. So is this true? I'll just wait for maybe a couple of minutes. If any of you solve this, can raise your hand.
And how we'll go through this problem? Which one we will use?
So
No, we have to use x transpose of inverse into xy.
is it? Yeah, you can check.
Yes, ma'am. We
Or
are
do you?
calculating. We are
Okay.
That is true.
It's true. How did you find it?
The
Yes,
W
ma'am, it's
formula
true.
is xtx of that inverse and then xty. So if you just substitute the values, then you get 3 minus 5.
Okay. All right. Yeah, so that's correct. So here, what you could have also done is you could have also like just check for what is your since you wanted to minimize this objective function, right? This is x transpose w minus y, right? Whole square. So you could have checked what is x transpose w minus y, and but also like we may not know. All right, I mean this is fine. Whatever you have done. So you have found this w star, right? X transpose inverse xy.
Yes, ma'am.
Okay, fine. Okay.
Ma'am, what to do, ma'am? First,
Hmm.
x transpose and then find the inverse and multiply with xy, right?
Yes.
What you written on the above?
That is just x transpose w star minus y. So if you
Oh,
do this,
hmm.
what you will get is just 0.
Yeah.
So if
Oh,
you
that
get
is
this as
scalar.
0, hmm,
Okay, okay.
okay. So yes, this is true. So let's go. This is my question number 2. So here the question is that you have 1000 training samples and you want to compute 10-fold cross validation error. Okay. So to calculate this, you have taken the average of the errors obtained from n1 iteration of the cross validation process. So you have to find your n1, n2, and n3 in this question. It's very simple. There is no calculation involved.
How we go through, ma'am?
100
100 is what?
in each group, in each fold.
100 will be in each group, correct? So you have 1000 total points and you want to do it 10 folds. So in every fold, F1, F2, F3, well, F10, you will have 100 data points. That is true. But now the question is, how many iterations would you do to calculate this error?
10.
10 iteration. Now, each iteration involved training a model on a subset of size N2 of the training data. So what is this N2? Like, what do you think
9
this
is to 1.
N2?
900 is to 100.
900. 900 is 200. Correct. right? Because 10 minus 1 fold you will use for training. I mean, the data points that are there in those folds you will use for training, and whatever is remaining you will use it for validation. So there were 1000 training examples, so 900 you will use for training and 100 you will use for um, validation. Very simple question. Okay. Now next is based on Gaussian kernel regression. So I will just write the kernel regression function for you, Gaussian kernel
One thing,
for you.
ma'am.
Hmm.
Go to the question first, ma'am.
Okay.
Uh, Ma'am, I'm confused every time how to do write X, ma'am. Row wise or column wise. That is the initial confusion for me.
Okay. So here your x is what? So x is your x1 and x2. Right? And this would be this would be 4 cross
2 cross 4.
wait. Not 2 cross 4, no. This is 4 cross 2.
4 cross 2.
Wait. This is 4 cross 1, so it should be 2 cross 4, correct?
X1 and X2 are features here.
Hmm?
X1 and
No,
X2 are
here,
features.
no, here it is not like that. So here you have this is 4 cross 1, no? Okay. So you have here 1, 1, 1 minus 1, minus 1, 1, and minus 1, minus 1. Okay. And your y is minus 2, 8, minus 8, 2. All right.
So,
So,
ma'am, X1 and X2 are making the features, and
yes, features, correct.
And the data is the column and the feature is row.
The data is the
Column
column.
and a feature is row, right?
This is, I can write it like this.
That is feature X1 and X row.
They are in row.
Column is the data of features.
Hmm. Yeah.
Okay. And then how calculate X and Y, ma'am? X into Y. Simply
X, in,
dot product.
X into Y, how will you do it?
X
Matrix
Y.
multiplication.
No, it's a multiplication, not a dot
Matrix
product.
multiplication.
matrix multiplication.
You can do this, right?
Okay. Row and their column, row and column. Okay. Thank you.
X is always D cross M. Is that right? In these formulas?
X is always D cross, yes. Okay. So here in this question, you have the Gaussian kernel regression is performed for this data set. You have X, you have Y given to you. Alpha is given to you, and um, you have to find the prediction for this
Ma'am,
point 1 comma 1.
it would be 2.
It will be 2.
Yes, ma'am.
Okay.
Because it comes from data set. Already it's given.
Mm, what is given and what is coming from data set?
Actually, we have to predict 1 1. So it's present in third column, and its label is 2.
Okay.
So it would be 2.
No. Yeah, you do it again.
Three, is it?
Free is correct.
No, ma'am, actually I used binary classification. That's why it's my wrong answer.
Hmm.
Ma'am, which formula is to use, ma'am?
Which formula to use?
Yes, ma'am. Which formula is need to use to solve this question?
This is a formula that we're going to use.
Right, summation of. Oh,
So how do we solve for certain question? These questions like this. So we have to predict for this. You have X test to be 1 1, right? And the prediction for this 1 1 is going to be sum over alpha I kernel of xi with x test, right? I is varying from 1 to 4. Now, if we are using the Gaussian kernel regression here, then in that case, my kernel function, so k of xi comma xj, is going to be e to the power minus xi minus xj norm square divided by 2 sigma square. Now, sigma square is given to you as 1 by 2. So this term goes to 1. So we can just remove this. Now you know what your x test is. You know what your xi's are. So this is your this one, this one, this one, and this one. So what is okay. So what is alpha 1? This is 2.1 times k of xi, which is 1 0, 1 0, and 1 1. Right? Plus minus 2.1. So this is minus 2.1 k of 0 1 comma 1 1. Then plus 3 times k of 1 1 comma 1 1 plus 0 times, so we can just ignore it. Now if we find k of 1 0 comma 1 1, it is going to be what? This is going to be e to the power minus of 1, right? So xi is 1 0 minus 1 1, so you get 1 square, so which is 1. So 2.1 times e inverse minus 2.1, even this will be e to the power minus 1, right? So this also gets cancelled out, and all you are left with is this. So this is 3 times the kernel of 1 comma 1 1 comma 1 1. So 1 1, so this is what this is, also 0. So e to the power 0 is just 1. So you are left with just 3. So this is how you can do it. All right.
This 3, how it is norm of?
No, this 3 is 3 times this, right? So kernel of so this k of 1 comma 1 1 is just going to be e to the power minus of norm square of xi minus xj. So 1 minus 1 0, 1 minus 1 0. Basically, you got 0. So e to the power 0 is just
Okay,
1.
okay,
No?
3. Yes.
So you just that's how you got 3.
In the formula of Gaussian kernel that is given here, k of xij equals to what is here xi and xj? Xi is a test data point or from the training data set?
Any xi, any xj we are talking about. But now here we have x test. I mean, when you're finding the prediction for this point, so 1 is your x test. I mean, so 1 1 I have taken everywhere. No,
Yeah,
1
ma'am.
1. So these are your x test.
And the
These are
formula of
coming
Gaussian
from
kernel is exponential.
exponential e to the power e to the power minus of a norm of
Xi.
xi minus xj square divided by 2 sigma square.
Okay, 2 sigma square. Okay, ma'am. Thank you.
So do you also know that this kernel matrix that you get is how can you find this kernel matrix? This kernel matrix is, if let's say if you have
K,
two
xi,
data point,
x1.
kx1 x1 kx1 x2 and so on, you can keep going. So k of x2 x1, k of x2 x2, so on, right? This is how you can write the kernel matrix. Okay.
Ma'am, in this case, x1 we take it from the training data or test it.
X1 you're talking this one you're talking about for this k.
Yes, ma'am.
Training data.
Okay, ma'am.
So what is the answer for this question? So these questions, some questions are taken from your previous term. If you would have seen the previous term paper, some of these questions are taken from there. So what do you think the answer can be for this question?
B.
D.
Some people are saying B, some are saying D, but D is correct. Can you like if we take
Or
B,
zero training error, is it?
yeah, you want zero training error. So only if h of xi is y, then only you can get your zero training error, no? H of xi to be y.
Yes, ma'am, because it nullify.
H of xi minus yi whole square. I'm getting from 1 to 9. So D is correct. So here, what is being said is the map estimate for linear regression weights W is equivalent to ridge regression. So we have seen this, right? We just saw how can we reach to the ridge regression estimator. So what are the assumptions that has been made to find this? Can you recall this?
B and D.
Yes, ma'am,
B
B
and
and
D. Yeah. So the prior was taken as normal with mean 0, variance gamma square, and by given xi was following normal with mean W transpose xi and sigma square. Okay. Question number 6. So you have your x and y given to you, and the rich penalty is assumed to be 50. So what should be the value of this W hat rich divided by W hat ml? So what is W hat rich? You try it first. Okay.
Yes, ma'am. 1 by 2.
1 by 2.
Yes, ma'am. Answer would be 1 by 2.
Okay. Is it clear for everyone?
No, ma'am. Solve, ma'am.
Did you try?
I'm not able to solve that question, ma'am.
Okay, so what is your W hat rich? Can you tell me? What is W hat R?
Yes, ma'am. X transpose X plus reach penalty into I over the inverse XY.
And what is W hat ML? It is X
W hat ML is
transpose.
only X transpose of inverse XY.
Now, what is your lambda is given to you as 50, right? So what is XX transpose?
It would be 50 XX transpose.
XX transpose would be 50. 50 plus 50 would be basically 100, right? So 100 ka inverse would be 1 upon 100,
Yes, ma'am.
right? And in the, I mean, even if you solve for xy, you are going to get some constant. I mean, some
Yes, ma'am. Just cancel it.
cancel it out. You'll have 1 upon 50. So what you get is just 1 upon 2, which is 0.5.
Yes, ma'am.
Yeah. So this is also very simple. Like if you know what is W hat rich, you know what is W hat MLE, you can easily solve this problem. Okay. Right, so this is another kernel regression question, but here now the kernel that was used is different. Now here you have polynomial kernel. You have to, in this question, you have to make the prediction for the data point, this.
It would be 1.
1. Okay.
How we
Hmm. Anyone else?
Yes, ma'am. How?
How?
Yes, how to solve?
Mm. See, we had seen that this prediction is for any data point, any X test, can be given by sum over alpha I kernel of xi comma x test, right? I varying from 1 to 4. Now here you have a polynomial kernel of degree 3. So basically you have defined your xi xj to be 1 plus x transpose xi xj, right? Xi xj to the power 3, right? Now if you, since your x test is given to you as all zeros, so if you find this k of xi comma x test for any xi, right, for this x test, you are
Is one.
always going to get 1, right? You're always going to get 1. So you will get alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is the prediction. Now all these alphas are given to us here, and when you add all of this, what do you get? So 1.3 plus zero point 0.6, you have 1.9. 1.9 minus zero point 0.9, which is just 1. So the answer is 1.
Yes, ma'am. Understood.
Like, ma'am, all this kernel has to go to zero.
Uh, no, what we said is, see, we are not given the data set, right? But what we are given is all this X test, all the values are 0, right? So if you, when you do your xi xj, you know you are going to get 0, right? So
Mm.
1 plus this 0 ka cube is just going to be 1. So
Yes.
k of x1 comma x test is equal to 1, k of x2 comma x test is equal to 1, and so on. So that is why this value turned out to be just the summation of all these alphas, and that is just 1.
So whatever zero transpose, this is our extension.
Yeah, correct. Because we have to do the prediction for this data point, right? Like when we did the Gaussian kernel, we're talking about the Gaussian kernel. There, my X test was 1 transpose. Okay.
What was your last point? What was one transpose? Can you please go?
No. What I was saying is, in this question you have X test. I mean, we wanted to predict for this data point.
No, this question is clear.
Huh.
The last.
In the last question, we wanted to predict for this data point. So that is my X test.
Okay, this is okay. Previous. Okay.
No, we're just saying that why is it X test? So
Can you please go back to that question?
the exponential one, this one.
Yeah. This third one, how did you get? Like 1111?
Third one, this one.
Yeah, 1111.
Huh.
1111.
Because your X3, now you have to do X3, no? So X3 is this, right? This is my third data point. So X3 comma X test. X test is 1 1. So 1 1 comma 1 1.
Okay.
And we didn't take X4 comma X test because the alpha 4 is given to us as 0. So we just ignored that,
Thank you.
the fourth one. Okay. So that was all I had for today. Um, so
Hello, can I share my screen? I have some questions.
you can share your screen. Yeah, let me just stop sharing. Yeah, you can share your screen.
Okay, ma'am. Ma'am, in this question,
Which question? The training.
yes, ma'am.
This is okay. This is you're talking about week
No. Sorry,
7.
sorry. It's a binary classification.
Mm,
Yeah, ma'am. In this question,
okay. Training data set for what is this timer running through?
no, ma'am.
Yes.
It's actually QP sites
Okay, okay.
for
First one.
practicing Pilates.
First one.
Okay, okay, okay. Training data set. Best linear.
Square is better than cube.
Why, ma'am, square is better than cube?
Oh, hold
It's
on.
Pythagoras.
Due to model is linear.
It will remove all the negative signs.
So, okay. If you do W transpose Xi minus Yi square, so what do you get there?
W1 is better
W1
because
is better. Yeah.
it's because for the W2 it's a cube root and therefore the variance will be more compared to the first one. Data spread will be more for the second, and that's why it will have
Yeah,
more
you
error.
have to work it out, no? This part, W transpose Xi minus Wi, you have to like open the bracket and work it out.
Okay, ma'am.
Uh, can
Ma'am,
I
could you
get
please
that
explain?
link?
Hello, ma'am. Uh,
Mm-hmm. Yeah.
could you please explain this question?
Okay. Adding a feature, dataset, analyzing.
Dummy feature.
First one.
Yeah, I know the answer, but why? What is the reason behind this?
Ma'am, I think when we add this dummy feature, the line will not pass through the origin, because if we do not add dummy feature, then it will W transpose X line passes through the origin, and and therefore we will see like more error. But when you add dummy feature, and then we are kind of shifting that line upward or down.
Okay.
Ma'am, in this question, there are two options are correct. First one and the last one. that the training the kernel regression model of degree 2.
Um, this is which term paper you're talking about?
Ma'am, it's 2020 through August 23 August.
The last. I want to check is the loss of the data.
Correct me if I'm wrong. Actually, like the dummy feature actually this helps in the problem of overfitting, and then this kernel degree, right? Actually, that will also help in it's of degree 2, so it
Degree
will
two.
capture more of patterns.
Yeah, that
Obviously,
is fine. That is
not the
adding
proof, but
atomic.
actually, obviously it's better because it's quadratic, so it will take it to
It
a
will
higher
fit.
dimension and find out more patterns.
It will fit more properly. That is the first one. I'm not little sure.
And we also use ridge regression and lasso for, so why option B and C is wrong? I think it's talking about training data set. That's why it might be wrong.
No, I don't think so.
Two and three gives more emphasis on regularization rather than giving uh, weightage on model weights. It should be a balance. So if you penalize it a lot, then emphasis on regularization more, either L1 or L2.
Okay. Ma'am, I have one last question I want to ask.
Yeah, you can go ahead.
Ma'am, this question. I'm have also its sub part. I'm
Can
showing.
you zoom it?
It's a question, but there's also a sub part. Um, yeah, the first one. If the next iteration of gradient descent is expressed as, what would be the value of k?
It will be 2.
It will be, yeah, 2 it will be, because here the step is sign is positive. Actually, it should be negative. So for that, we have to take the opposite.
Actually, W1, because it's talking about the descent, and W1, if you see
Yeah, right, right.
W1 and then descent would be just opposite to this, which is W2, and therefore it will be 2. Because it's talking about the,
It
if you
means
see specific,
it is in opposite direction.
yes, descent. If you recall from stress, we had this gradient descent and ascent from maths too.
Okay.
And this is gradient descent. That's why always opposite to the um, opposite to this unit vector. That's why
Okay.
it's
Thank
What is the link you're using?
Ma'am, QP question practice dot space.
There is a link like that. Can
yes,
you
ma'am.
share it
This
in the
is for
chat?
practice. This is
Can
How
you
do you
share
get
it
this?
in the
How do you
chat?
get this link?
Okay, ma'am, I'm sharing it.
How do you get this link?
Someone sent me.
So like this has all the QP for all the
yes, ma'am.
subject for all the term.
Starting for all the subjects.
This is all the subjects.
Yes, ma'am, all the subjects.
This is nice.
I think one of the students made this.
This is really nice.
Ma'am, just search for a question question practice. It's became on the top, ma'am.
Yeah, ma'am. I just give this in message.
Oh, okay. So it is all degree level courses and everything. Okay, that was nice.
Now, good thing is that it allows in practice mode. The timer that you saw. So that
So it shows you like how much time you're taking to solve the
Yes,
paper.
ma'am.
yes,
It's best for exam.
Nice.
it also has got inbuilt the scientific calculator,
Yeah.
And
which
this
we can.
calculator is better than when you get a TCS.
No, it's same.
Same
That's
one?
why we can actually practice here, because in
Ah,
our quiz we have different kind of calculator. I mean, in this
okay.
portal, study portal.
Okay. Mhm. So if I 5 papers, so okay, maybe we can
5 papers,
close
ma'am, but
this
then
session.
it
Yeah.
will be same. There may be same like 2-3 papers.
Okay, okay. Okay, that's nice. All right. Thank you, everyone. We'll close this now. So join the sessions that are happening tomorrow, day after, and the day after. So all the previous terms questions will be discussed there.
Ma'am, if you have any idea about this BS MTech program? What is this all about? If in 2 minutes, if you can explain.
Base Sempic.
BS MTech
For
upgrades.
for M.Tech, sir has told in a Sutra 2.0 in NIT Patna. You have attended that